Now, the European Extremely Large Telescope is taking shape in the Atacama Desert in Chile, not too far away from where the European Southern Observatory have the Paranal Observatory, which is home to the world's most amazing telescopes at the moment. And I just thought that we'd just do a little bit about the ELT. Why at the moment? Well, because they've just released a new photograph of the observatory under construction. And they don't tend to release these photographs very often. Perhaps they think nobody's interested, but they don't tend to take that many photos of the ELT under construction. But they've released a new one this month. So I thought that might be a nice opportunity to have a look at the what will be, when it's completed, the world's biggest ever telescope, and this being the European Extremely Large Telescope, the world's biggest eye on the sky. Um, now, as I said, it's being built in the Atacama Desert in Chile, and it's billed by the European Southern Observatory as a dazzling new future, and it's being built at Cerro Amazonas in Chile. And just to let you know where it is, that's the Paranal Observatory. There, you can just see the domes on top of the mountain there, and this is what it looks like. There's the famous Paranal Observatory, and Amazonas is just, well, not a stone's throw, but it's not that far away. So this will be where the ELT will be, what is being built at the moment. Now, just a bit of data about this telescope. It has a main mirror of 39 meters. Originally, the mirror was going to be 42 meters, but Europe discovered that if they dispensed with the outer ring of the mirror segments, because there are 798 mirror segments in the main mirror, if they did away with the outer ring of segments and cut the diameter of the mirror from 42 down to 39 meters, they could save nearly €1 billion. So that's what they decided to do. As it stands, the telescope has a collecting area of 978 square meters. Now, all of those 798 mirror segments have to be aligned absolutely perfectly. The tolerance to which they have to be aligned is tens of nanometers, 10,000 times thinner than a human hair across the whole of the mirror. So that is an unbelievable accuracy that they have to achieve. And they have 4,608 sensors across the mirror measuring the relative positions of those segments and correcting them in real time if any get out of alignment. And the primary mirror weighs 132 tons. It's made of a glass ceramic compound called Zero Dur, and the total weight of all the mirrors is 140 tons. So this is a huge project that Europe has undertaken to build the world's biggest telescope. Now, let's have a look at the science goals of the telescope. Firstly, it's going to be used for imaging exoplanets directly and analyzing their atmospheres. And this has never been possible with an earthbound telescope before, but the exquisite light gathering power of the ELT will be enough to enable it to see exoplanets directly and analyze their atmospheres, much as the James Webb is doing at the moment with some of the exoplanets, as we were hearing recently from Roger about the TRAPPIST system. And this is the first time in history that technology of an earthbound telescope has been able to do this. The whole telescope is reckoned to have a resolution 15 times greater than the Hubble Space Telescope. So it just goes to show that putting telescopes in space is a great idea, but the technology for ground-based telescopes has caught up so much that the ELT will have an expected 15 times the resolution of the Hubble Space Telescope, and thus enable it to look at exoplanets directly. In terms of the solar system, well, it's going to be doing extensive survey work in the solar system and probing, among other things, the Kuiper Belt, other rocky objects, And it's going to enable us to see objects in the solar system with a telescope in far greater detail than we've ever managed to see before. The observation of stars is going to be important as well. The ELT will embark on a program of helping us to understand more about the birth, life, and death of stars, and also the link between the evolution of stars and the elusive dark matter. And that hopefully will enable us to answer some fundamental questions. Talking of dark matter, the ELT will also be used to find or identify what the dark matter is. I won't say find because we know exactly where the dark matter is, but we don't know what it is. And as we were saying last week when we were talking about Euclid, the universe is only 5% made up of matter that we can see and measure directly. The rest of it is this so-called dark universe of dark matter and dark energy. Also, the ELT is going to be used to probe some of what are considered constants in the universe, the so-called physical constants. And they want to use the ELT to try and test whether some of these constants that the astronomers and astrophysics use are actual constants or whether they vary over time. So that's some pretty fundamental work that it's going to be doing on those. And of course, expect the unexpected, because they will undoubtedly be things that the ELT discovers that we had no idea were there at all. So that's a big science program ahead of the ELT. Let's look at the telescope itself in a little more detail. The telescope is made up of a 5-mirror system. As we said, a 39-meter segmented mirror of 798 fragments, then a 4.2-meter diameter secondary mirror that the light goes to next. Then there's a thing called a tertiary mirror, which is 3.8 meters in diameter. Then it goes to a fourth mirror, which is a flat mirror of 2.4 meters. Then it goes to a fifth mirror, measuring 2.7 by 2.1 meters. And then the light exits to the right of the telescope to the science instrument platform, where there will be lots of very, very advanced scientific instruments used to analyze that light. So it's quite a complex optical system, but this is what the astronomers and the engineers have come up with.
Sounds like a complicated collimation job.
Yeah, I would think so. Yeah, I hope they've got a laser or something handy to collimate that. And if you want to know what a 39 meter mirror actually looks like, they've done using these sort of cardboard hexagons. They laid this out to show you just how vast that primary mirror actually is. That's quite an amazingly large mirror.
Amazing.
And if you want to know how big the observatory will be, well, this is the observatory compared to Big Ben. So as you can see, it's big. And if you want to get a comparison for landmarks in your country, go to the website of the European Southern Observatory, and they've got the observatory compared to lots of other landmarks around the world. But as you can see, it's going to be it's going to be absolutely enormous. Here's a very short video where we fly into the ELT by the wonders of computer graphics, and I just think this is going to be like a huge cathedral of astronomy. That's the only way you can describe it. It's the size of a cathedral. So let's take a flight into the ELT. Okay, so that was a flight into the ELT. Sorry if that video was a bit jerky in places. The first step in building this massive observatory was blowing the top off a mountain and lowering the top of the mountain by 40 meters to create an area to build the observatory on. This happened on the 19th of June 2014. So that was the explosion blowing the pointy bit off the mountain. And then the top was flattened. The access road up to it was built, which obviously took a while. And the foundations were dug by October 2018. Then the foundations for the steel rebar for the dome and everything was put in September 2000, by September 2019. This was the picture in January 2022. The whole project, of course, got delayed by the COVID epidemic. So work had to stop for a while. But as you can see, by January 2022, they were making good progress. And this was November last year. And then the most recent photograph from the site, taken this month, you can see that they've moved on astoundingly well. So this is what the ELT now looks like. And the first light of the telescope, because of the delay for COVID, it was originally going to be 2025. It's now set for 2028. So there you are. So that is the extremely large telescope. And it's stunning, guys, isn't it? I mean, the sheer scale of it is just absolutely unbelievable.
Yeah, as you say, I'm just imagining, because it's got that adaptive optics thing within it, where all the mirrors have got actuators underneath them, and they fire a laser into the sky, and of course it adapts to what the actual atmosphere is doing so fast. I mean, it's an amazing piece of kit. It's absolutely fantastic.
I did a little calculation from what you were saying about Hubble resolution.
Yeah.
And it turns out that with the adaptive optics, it will have a spatial resolution of 0.00093 arc seconds.
Wow.
Well, that's not very good, is it?
We could do better.
Never satisfied, Daz. You're never happy.
Andy,
There's always room for improvement.
Can you compare that?
Andy,
Sorry?
you were talking about the outer mirrors that
Yes.
taken to make it 39 meters, and there was another telescope called the Overwhelmingly Large Telescope.
Yeah, the owl, yes.
OWL.
Yeah.
Like the acronym.
Followed by the ridiculously large, the RLT. Isn't that?
Okay, yeah.
I always thought
Shouldn't the owl one be at Hogwarts?
Oh, very good.
Very good. I always thought they should have made one called the Superb Owl or Super Bowl. So that would have been good. In terms of resolution, Luke, can you compare that angular resolution to something? What was it for the James Webb, for example? Anybody remember?
James Webb is, of course, it's wavelength dependent, right?
Yes, of course.
Right. But the number that's often given, I think, is 0.032 arc seconds.
So,
and Hubble would be 0.014, actually a little better, but again,
it's wavelength dependent.
Wavelength dependent, yes.
Yeah, sure. There we are then. So, we're looking forward to the ELT. Can't wait to see the results from that. As I said, it's going to see first light now in 2028 if all goes well. I would love to have that on my bucket list, to pay that a visit, just to stand in that dome. I mean, can you imagine what it must be like?
I'll come with you, Andy.
Yeah, well, that's it. That's a date then, Michael. We'll do it.
We need more coffee money.
Ian says he can't.
Lots of coffee money for
Ian
that.
says he can't wait till the BLT.
Yes, absolutely. Yeah. So
the BLT. Ian wants a BLT.
So, if you're wondering, viewers, how that whole adaptive optic system works, see, the thing is, up in the high atmosphere, there's a layer of sodium atoms, and if you shine a laser at the sodium atoms, they fluoresce under laser light, and in the sky it looks like an artificial star. Now, the big problem with telescopes, as we all know as astronomers, is that the atmosphere never stands still, that it's got currents of air moving about continuously, which spoil the viewing. So there's another small telescope which will look at those artificial stars, and the ELT will have 8 lasers, so it will create 8 artificial stars. And they will be monitored in real time. And the movement of the atmosphere counteracted by applying a signal to each of the actuators that are behind each individual segment of that mirror. And they will move in the opposite way to what the atmosphere is doing, thus cancelling out the movement, which will give you an ultra stable image, even if the atmosphere is quite turbulent.